We've already talked about electric charges. So you have a charge Q and you have another charge Q over here, and there's going to be a force between them. We know the force is going to be the electrostatic charge Q1 Q2 over R squared. If that's Q1, that's Q2, and the distance between is R. Well, that raises some interesting ideas for us. For example, if we have a charge right here, I'm going to just call it Q1, okay? Or just to make it easy on us, I'm just going to call this maybe big Q, capital Q. And we have another little charge over here, small q. And so that charge is experiencing a force, due to the other charge, Q, big Q. So we can imagine this as being a little small charge of some sort. In fact, the book calls it a test particle or a test charge. And so this is like theoretically, you say if you put it there, it has a force of KQQ over R squared. Okay, now if I move this, however, so that it's some distance R on the other side over here, then it has the exact same force right there. If I put it some distance R above, it has the exact same force. If I put it some distance R below, it's got the exact same force. In fact, if I have this charge here, if I take my little charge Q and put it anywhere on the surface of a sphere of radius R surrounding that other charge, then it experiences the same force. The only thing is it's pointed outwards in some direction. So we could say that force F sub E, is going to be K, Q, Q over R squared with R hat, the unit vector, being the unit vector pointing outwards. So there we have an expression. Well, this is nothing new. This is what we had, from chapter 21. Well, the thing is, if I have charge Q here, radius R on the sphere, and I put some little charge Q there, if I put a different charge Q out there, the force is going to be different. And so the only thing that changes is that charge right there. So we could say that the force acting on that charge, so the force acting on that charge is K big Q over R squared times little q, and if I change this, I've changed that. And so all of this stays the same. Okay, so we could look at that and say, no, wait, that's all staying the same. Okay, so I could just replace that with a constant and then multiply the little q times that constant, and that would tell you the force everywhere on the surface of that sphere. Now, why would we do that? Well, this all goes all the way back to Isaac Newton and how he conceived of this as this charge, or he was thinking of gravity, with a mass in the middle, influencing space around here. And now, if I were to have it at a different distance, then the influence would be spread out a little bit differently, and so the force would be bigger. And so, but there's nothing actually connecting the two charges. There's just empty space between them. So Isaac Newton introduces the idea that somehow this charge, or again, he was discussing mass, the mass of the Earth, for example, is influencing space around it, which is why the moon goes around, it experiences a force, even though there's not like a rope connecting the Earth to the moon. And so he introduces the idea of a gravitational field. So we can do that too. This is an electric field. In physics, we call it a force field. Okay, so the force field is this region of space where if you put something in the presence of this other charge, it experiences a force. So it's a field of forces. So we could then say the force is going to be E times Q. Now again, if we want to do this in vectors, this was like r hat, and so we would then say that the force field or the electric force field due to that point charge, the electric force field due to the point charge would be K times Q over r squared in the r hat direction. And so this is our expression here, and we know the relationship between force and charge is given by that. The force is equal to the charge times the electric field. And so we would symbolically draw the electric field and say, we have an electric field like this, and these are what we call electric field lines, and they are symbolic that if you were to put a positive charge in here, that positive charge would experience a force in the direction of the field lines. Okay, so positive charge, direction of force, the field lines. If I were to put a negative charge in there, it would have a force that way. This is consistent with our idea that F equals QE. So the electric field lines that I draw there are basically graphical ways of describing this electric field. And so the force is just Q times E. Okay, so if I have an electric field this way, pointing up, that means a positive charge would have a force up. A negative charge would have a force down. And so again, these are the electric field lines. And so the field lines are your graphical sort of way of describing it. Another interesting thing about these field lines, if I have a positive charge, any other positive charge I put near it is going to be pushed away. So that means the field lines are all going to go away from here. And so one of the things you notice is that as you draw lines going away, the lines are closer together if you're up close and farther away if you happen to be farther away. So that's an interesting sort of thing. The density of the field lines, how close they are together, tend to relate to the strength of the electric field. So we would say a strong electric field we would symbolize by having really close together field lines, and a weak electric field we would symbolize by having really far apart electric field lines. Okay. Now, if we have a negative charge and I put a positive charge near it, it's going to have a force this way. And so what you find is that the electric field lines tend to go towards negative charges and go away from positive charges. Okay, so if I had like metal plates and I had this metal plate as positive, that metal plate with negative charge, then the electric field lines would go from the positive to the negative. Okay, the other way around if the top plate was negative and the bottom plate was positive. So we've got both the idea here of electric charge creating an electric field and then electric field lines. Now, one other thing I want to mention here is, what if we have a situation in which we have two positive charges? Now, obviously, the field lines are going to go away from each charge. But over here somewhere, it's being repelled stronger that way than it is this way. But you do have a vector sum of the two, and so that means the field line would be pointed like that. So that means the field lines would curve in between here. In fact, right in the middle, the forces cancel, and so the electric field is zero in there. And so the field lines would curve this way. Okay. So that would be for two positive charges. What about if we had a positive charge and a negative charge. Well, obviously, on a line between the two, everywhere between the two, there's a force repelling from the positive going towards the negative. Because you're closer to the positive charge on the left, then it's going to repel more than negative attracts. On the right, you're closer to the negative, so it attracts there. In between, if you're dead center in between, then this one's repelling like that, this one's attracting like that, and so the up and down components of the vector balance out, and you're going this way. If you're over here, this attracts more than that repels, and so the vector sum is at an angle like that. So what would happen is the electric field lines would leave the positive charge, enter the negative charge here, like that. Okay. So that means if you were to put a positive charge right there, it has a force tangent to that field line. A positive charge here would have a force tangent to that field line. And so what happens is that anywhere in here, a positive charge is tangent to the field lines, okay? And so that's a way of using this. Now, this gives you an interesting graphical way of doing it. Whenever you have a positive charge, field lines go away from the positive charge. Whenever you have a negative charge, field lines go towards the negative charge. Now, you can never get, if you got charges out here, you can never get a field line just starting somewhere. The field line must always start at a positive charge and must always end at a negative charge somehow. Okay. That's really not what it would look like in this case, but more like that. But you get the idea that field lines must always start with positive charge. They must always end with negative charge. You can never get two field lines crossing each other. It can't do that because anything going right there, if it's experiencing force this way and that way, that's a force that way, and so the field line should be like that. Okay. Those are the basic idea of electric field lines. And so the electric field lines are a graphical visual tool for how you see things. Again, suppose you have a line of positive charge and a negative point charge. What would happen is the electric field lines would kind of leave the positive here and go towards the negative. And so, again, you could graphically do this. Now using the rules for how, again, looking again in the book, but using the rules like I've described here for how you draw the field lines, without doing the math of solving this, and we're going to do some mathematical problems soon here, and you see how difficult they can be. Sometimes just drawing the field lines gives you a rough idea of the strength of the field and the direction of the field. This would suggest the field is strong, the forces are stronger near there, directing towards that, and the forces are weaker out over here. And so, again, the direction, the forces are given by tangents to the field lines. The field lines always originate from the positive. They always terminate at the negative. And so that gives you the basic rules. That gives you how the field lines work. And so this lecture has introduced the idea of the electric field. I've also derived the electric field due to a point charge. So we've derived the idea of electric field. So the electric field F equals QE, where the electric field relates to the force, and the electric field due to a point charge is K sub B Q over R squared, R hat, so it's a vector. So that's the electric field of a point charge. And then I introduced the idea of electric field lines. So I've actually, in this one lecture, covered several sections here of chapter 22. So now let's start doing some numeric example problems.